Welcome to lesson number 5 on precision and significant figures. Our objectives for this lesson: identify the precision of a measuring device and identify the amount of significant figures in a number. So let's first talk about accuracy versus precision. Accuracy is how close measurements are to the accepted or the true value, and we can measure that using percent error. And our precision is how close the series of measurements are to each other, and we can measure that using standard deviation. So looking at this example here, we have 3 targets. In this first target, like all of them, the goal is to get to the bullseye, the center. And so all the arrows are touching the bullseye. So that's our intended target. So that is a very accurate shot. Precision is how close the measurements are to each other, and they're not that close to each other. So therefore, this is not very precise. Next example, all of the arrows are very close to each other. So we can say it has high precision, or they're very precise. But we're not in the intended target, so it's not very accurate. And last, we have both. We've hit the intended target, so it's accurate, and all the shots are close to each other, so it's very precise. So this is what we're shooting for when we make measurements, to be both accurate and precise. Here's another example. These students were asked to determine the density of sucrose. So the known density of sucrose is 1.59 grams per centimeters cubed. So out of the 3 students, students A, B, and C, which student is more accurate? So you see that they have 3 trials. Which one of these students is most accurate? So again, accuracy is how close you are to the actual value. So who has the closest measurements that are close to the actual value or the actual density? Well, if you look at the average of all 3 students, 1.57, 1.51, and 1.70, who's the closest? Student A. So student A is the most accurate in terms of their measurements to the actual value. Okay, now let's look at significant figures. Okay, so when we make calculations or do calculations, so like scientists, we can only be as precise as the least precise measurement that we have. So another way of thinking about this is you're only as strong as your weakest link. So what we do is we count digits in any measured number to determine the level of precision of that measurement. So for example, if we're trying to measure length of this paperclip using this ruler, this measuring device has an inherent amount of precision. Some devices are more precise and some are less precise. So significant figures indicate the precision of a measurement. So when we make a measurement, the sig figs that we have include what is known as the known digits and then a final estimated digit. And that estimated digit is the precision of the instrument. So this is a centimeter ruler. And so here we have 3 centimeters. So we know the paperclip is more than 3 centimeters. And then these are our millimeters, so 3.1, 3.2. And we can see that it's just past the 3.2 mark. So it is known, everyone can agree, that it's at least 3.2 centimeters. Those are the known digits. So then the last digit is going to be the estimated digit. And that's where there's going to be some variation between all of the students using this measurement. So I got 3.21 centimeters. I got that it's just past this 2 millimeter mark here. But some of you may have 3.22 or 3.23 centimeters. And those are all correct measurements because that last digit is the estimated digit. And that's the precision of the instrument. So in this case, this instrument, this ruler, is precise to the nearest hundredth place or nearest hundredth of a centimeter. Here's 2 more examples. So this is not as precise as the previous measuring device. This goes by tens. And so really what happens is when we have a measuring device, we always estimate 1 place past the smallest division. So if you go back here, the smallest division is going to be tenths. So we estimate to the next place value, which is the hundredths. Here, this is going by tens. So we're going to estimate to the next place value, which is going to be the ones place. So this line here then is at least 60 are known, and then our estimate is going to be the ones place. So I would say it's probably about 65. We could say 67. Again, that ones place value is going to be the estimated place value. This measuring device is much more precise than this. This is going by nearest tenth. And so we're going to estimate to the next place value, which is going to be the hundredth place value. So this line here is 0.4, and I would say it's almost to 0.5, so I'd say 0.4, let's say 7 or 0.48. And so if we say it's 0.48, again, that 100th place, that estimated digit, is where we'll have some variation in our measurements. So let's check your understanding. Can you identify the precision of a measuring device? Okay, so what are the rules then for counting up significant figures in a number? So when we get a number, how do we know how precise it is? Well, that's the sig figs, and how do we count them? Well, a couple of rules to remember. All natural numbers are any number that is not 0, so 1 through 9. We count those as 1 sig fig. So for example, 569 has 1, 2, 3 natural numbers. It has 3 sig figs. This one here has 1, 2, 3, 4 natural numbers, 4 sig figs. Okay, now the number 0. This is tricky. Zeros always count when they're stuck between natural numbers. They're trapped in there. So for example, see how the 0 is stuck in between 1 and 9? That automatically makes it significant. So this has 1, 2, 3 significant figures. And this number here has those trapped zeros as well. So it has 1, 2, 3, 4, 5 significant figures. Okay, what about zeros in the beginning of number or zeros at the end? All right, and this is, I said, where the zeros kind of get a little tricky, and you have to just bear with me a moment. So zeros before a decimal and a natural number never are significant. So for example here, 0.00789. These are just placeholders. Okay, they're not involved in how precise the measurement is, and therefore they will never be significant. So this number has only 1, 2, 3 significant figures. And in this number here, again, we have the 2 zeros out in front, so we don't count those, so it has 1, 2, 3, 4 significant figures. What about zeros after the last natural number? So here's my last natural number, 2. So this 0 here is only significant if there's a decimal point somewhere in the number. So there's a decimal point right here, so we're going to count that 0 as being significant. So we go 1, 2, 3, 4, 5 significant figures. This number here, this 0 is not significant because there is no decimal point in this number. So we only count the 1, the 1, the 4, and the 2. So that's 1, 2, 3, 4 significant figures. So let's recap that. So when I want to count significant figures, here's what I do. I start counting from left to right at the first natural number, the first non-zero. Okay, so going back here, if I wanted to count this up, I start counting at the first natural number, which is going to be the 7. The second step, if the decimal point is somewhere in the number, then you count any of those trailing zeros. Those are the zeros after the last natural number. So again, going back here, there's a decimal point here, so I'm going to count the trailing 0 here. No decimal point in this number, I don't count the trailing 0. Let's see some examples here. Okay, so start counting at the first non-zero, which is the 2 here. So I have 1, 2, 3, 4, 5. Now do I count these zeros? Yes, because there's a decimal point in the number. So 6, 7. So this is going to have 7 significant figures. This is a very precise measurement. Next one, start counting at the first non-zero, which is the 4. 1, 2, 3. And now there's no decimal point in this number, so I don't count this trailing 0 here. So it only has 3 significant figures. This is not as precise as this measurement. Next one, again, start counting at the first non-zero, which is the 4. So we exclude all these zeros here. So 1, 2, 3, this has 3 significant figures. What happens if we have something in scientific notation, where we have this exponent here? Well, when we have something in scientific notation, we only look at the front number here. So this is going to have 1, 2, 3 significant figures. And if I expanded this here into regular notation, 6.23 times 10 to the 6 is just 6,230,000. And so if we count it this way, we're still going to get 3 significant figures. There's no decimal point in this number, so we start counting at the first non-zero, 1, 2, 3, and then we don't count these zeros here, so it still has 3 significant figures. Okay, let's check your understanding. Can you identify the amount of sig figs in a number? At this point, you should be able to identify the precision of a measuring device and identify the amount of significant figures in a number.